Hey everyone, how is it going? So today we'll be seeing the 7 data embedding techniques for quantum machine learning using Pennylane, and those 7 techniques are these. So, but before we go that, I'll just tell you that we'll be working in Google Colab so that everyone is on the same page with respect to their system. And the first thing is obviously we need to install the Pennylane, and it's just as simple as pip install Pennylane. So let's do that. Some time. It's done, and let's import it now. So there's no error. So we will be just using the NumPy version of Pennylane and Pennylane itself. And yeah, so let's go and see the first encoding technique, the embedding technique. Okay, so the most basic type of embedding that you can use is the basis encoding or basis embedding. So the type of the data type that you can use here is for integer as well as binary values, because integer can be converted to binary values, right? And so now what you can do is you have these features, binary values of zeros or ones. Say you have n features of this sort, then it will be converted to, it would take n qubits to encode those n features. And so this is a little example that you see here. So say your feature vector just includes 1 and 1. These are just two values. Then it will be encoded to ket 1 1. These are ket 1 1 is just direct notation. It's basically a vector itself. And even if you're like done very simple quantum computing, then you must know the direct notations, right? Okay, so that's that. So now I will, before we just move on, I will just explain how uh, you know, uh, defining a circuit works in Pennylane, if you're not aware of, in case just maybe. So you can see this decorator we have here, and this is the Q node object, all right? So what the Q node actually does is that here it binds the circuit with the device that you will be executing the circuit on. So first here you can see I've just defined this QML device, Pennylane device, and I've just named the wires. Basically, mostly it's just the number of qubits that you would require. Then you can see I've just defined this function here. And although I have defined it as the basis encoder, the standard convention is to name it as circuit itself, because here is where you will be defining your entire circuit. But since I'm just showing you different encoding, the embedding techniques, so I just named it as basis encoder. So now the coding part is like super simple. You can just directly use QML.basis embedding, and you can directly pass on your data, your feature vector here, and this number of qubits, and that's it. Okay. So what you get here, what I'm returning here is QML.state, because I can show you the result just for that. But otherwise, what you would do here actually, that once you're done with the embedding part, you can just build your circuit on top of that. All right. So we just execute this, and it worked out well. And if I just do this again, so you can see I just got this vector, all right. And this tensor that I've gotten is just the ket 1 1, right? You can just pause the video and you can see it, right? Now again, say if you can directly also pass the integer value if you want. So for 1 1, the corresponding integer value would be 3. So if I just pass on 3, you can still see that I just get the same tensor. All right. So that's the most simple way of encoding your data for quantum machine learning. So now we will be moving on to more advanced technique, and with the increasing complexity. So that's for the first technique. Let's now move on to the next. So now let's get to the amplitude encoding. Again, this is a very popular and very well known technique. So the change here is that previously we were just using binary values to encode our data. But now if you see, we can use integer, float, or complex values to encode our data. And what it exactly does is that it encodes a normalized 2 to the power n dimensional feature vector into the state of n qubits. So again, we are just encoding our feature vector into the state of n qubits, but the way we are doing it, that's kind of different. So let's see it. So So again, you can see here I've defined the device here and the number of qubits for it, and then this little function that describes the embedding. Again, the coding part is super simple. You can just do qml.amplitude encoding. You can pass the data for it. You can pass the wires, this is the qubits, and then I'm just returning state so that I can just show you what the state is. Okay. So I executed it, and now this is the normal just feature that I just come up with. It's the normal uh, uh, vector, and you can see like there's nothing wrong with it. It's like very straightforward here. Like just what I passed was like actually a very good state that it could be. You can see this is the same thing that what I've got, but maybe like sometimes things might not be that good. So say you're dealing with the data where your feature vector is not of the size to the power n. So here if you see the size was 4, but maybe say is what if it's size 3, then what should you do? So let's see that scenario. So for that you can see again I have written a new circuit that I've named as Amplitude Encoder 1 here, and the only change here from the previous one is this one argument which is paired with equal to 0. So say if your feature vector size is 3, as you can see in the below example here, so it will pair the values with 0 to make it 2 to the power n feature vector. Now again, you can also set this value paired with equal to true, then it will apply a transformation on it. But if you just want to increase, paired with only zeros, then you can just pair it with equal to 0. Okay, so let's execute this part. So it's working well. You can see here for the feature vector, I have just 3 values, and when I just run it over, then what you expect is to get a feature vector of 4 because because that's the nearest 2 to the power n value. Okay, so that's for one case that if your feature vector is not of the size 2 to the power n. So one more condition that could pop up is when the bounds rule is not satisfied. So for every qubit, when you encode your data in these amplitudes, so alpha ket 0 plus beta ket 1. So alpha and beta, you are encoding basically your data in alpha and beta, but for that your alpha square plus beta square should be equal to 1. That's the most basic rule, the most basic version of the bonds rule. Alright, so what if that's not the case? Say, so for that, what you do is again, I just written a new code for that, new set of block of code that I've named here. The function as Amplitude Encoder 2. Again, the only change here is this argument normal is equal to true. So what it does is that it normalizes your feature vector so that this bonds rule is satisfied. That's just super simple to understand, I hope. Again, let's execute this part. And if I just, and you can see here that I'm actually passing a complex value. One is float. So let's just see, I just change this value to 2.5 and 1 and 1. But since I have passed normally is equal to true, if I just run this, you can see I still get a, I still get the output. It doesn't give me any errors, although, data types are different and it is a complex value as well. I have one. So that's the part. So it works for integer, float, and complex values. And this is the simple amplitude encoding. Now let's move on to the next one, which is the angle embedding or angle encoding. Okay, so now move on to the angle embedding. Again, you can see we can have as a data type integer, float, or complex values when we are using this particular encoding technique. And now again it encodes n features into the rotation angles of n qubits. Okay, and where n can be less than or equal to. So basically, even if you have say one value as in your feature, but you can use 3 qubits and you provide the same value to all those 3 qubits. That way. Okay. Now obviously, so again we do the same thing. We define the device, the number of qubits, and then I define this function that defines the particular embedding technique. Again, the coding part is simple. It's just QML dot angle embedding technique. Now, one important argument here is this rotation. So, what kind of rotation gate that you are using? So here, with this particular string value, you are defining that we want to use the Rx rotation gate. The other processes are Ry or Rz. And if you don't know what are these different gates, then you can check out the visually understanding the quantum computing playlist that I have on the channel that helps you to understand all of this visually. So probably that would help. Okay, so let's just again work this around. Let's run it. Okay, it runs successfully, and I just passed one value one as the data, and again it shows some uh, output. So uh, let's see how the circuit looks like. So this is a simple way of to have a look at your circuit in Pennylane. All right. So you can see here in the output below that first you are applying a simple Rx gate with the theta value as 1, and then what you're getting at the end is the state, because I'm returning the QML.state here, and that's what it's implying here. Okay, I think that was super simple to understand, but let's see what's happening behind the scene here. So if you see actually this particular array, so what is going on here is that actually this matrix that you see here is what actually defines the Rx gate. Okay, and I just know a dot in the dot product with 1 0, which actually defines the tag 0, which is the initial state. So I have just again kept the value as 1 here. That what I passed here 1. All right. So if you see here, I get the same output as what I'm getting from them. So basically, this is what's going on behind the scenes. Okay, Rx gate is nothing but a matrix. All right. And if you want to understand all of these into details, I highly recommend that you go through the visually understanding quantum computing playlist, where I use a simple Tkinter GUI software to help you visually understand all of these things. All right. So again, so basically, I hope this particular embedding technique is very clear. What you do is that you take a particular value of your feature value, and you just encode it as the theta value for the rotation gate, the Rx rotation gate. That was very simple and easy to understand techniques. But I think now all the simple techniques are done, and from the next one we are going to look into a little bit of complex embedding techniques. Okay, so let's go. So now the complexity starts. Okay. So now let's go to the displacement embedding. Again, you can have your data type as integer, float, or complex values. Doesn't matter. And what this does here is that it takes your end features and encodes it into the displacement amplitude R or phases phi. So that you have a choice there how you want to encode it. And basically, the name displacement comes from this d alpha, which is in fact the displacement gate, and this is the actually formula for it. Okay, so alpha is super simple. It's r into e to the power alpha, nothing complicated. The complicated part here is the a hat dagger and a hat itself, which are boson aggregation and annihilation operators. And if you haven't heard them before, it's all right. I will leave a link to the YouTube playlist uh, by the YouTube channel of Professor M. Does Science, who teaches all of this theory really well. And even if you know these operators, I think you should still check out that channel. It's a great resource to learn the quantum mechanics side of quantum computing. All right. So now you just have here, if you just substitute alpha equal to r into e to the power I phi in this particular formula equation, then what you get is this one. All right. And this is actually the how it's mentioned in the Pennylane documentation. So that's why I'm just showing this to you. Okay. Now let's move on. Okay. Basically, it's for multi-particle systems. So in a very simple way, if I tell you, So if you have like n number of particles, the creation operator actually increases the value by 1, and annihilation operator decreases the value by 1. In a very short way, this is the way to explain, I guess. Okay, so now if you get to the coding side, the very first difference is default.Gaussian here. Now we are having default.Gaussian, which is a simulator for the Gaussian continuous variable computation. Alright, so that's the very first difference here. Now, apart from this continuous computation, if you see the code here, again, it's like super simple. It's directly calling the function, the displacement embedding. You pass on to the features your data, then you pass on your qubits, or the bias. Now, other important part is here. So say if you this pass this method equal to phase, then what you are actually implying is that you want to encode your features, your data here into phi. Okay, so your value for your particular feature will be equal to phi, and your c equal your value for c will be actually r as well. Value for r. Now instead of method equal to phase, if you pass on amplitude here. So if I just change this to amplitude, now your feature vector will be used as a value for r in the Bow equation, and your this value that you are passing for c will be used for phi. So that's it. That's it. Very simple. And again, one another important thing is that you cannot get state here. Okay, this continuous, you cannot get state here. So what I'm doing here is just getting the expectation value for the number operator, which is the photon number, which is just one observable. All right, and I'm just getting the expectation value for it. So that's the simple circuit for this. If I work this, it's executed, and I just pass a simple feature vector. You can see I get one value here, and this is how actually the circuit looks like. Okay, and again you can see here that I am passing a complex value as well, but I am still getting the output. There's no error at all, and this little and that you see here, it just stands for the expectation value of the photon number. So that's it. That's the thing for this particular thing. And if you're not very clear with it, then it's all right. Just go through the resource that I'm linking in the description. But the aim was just for you to know that this thing exists. This type of embedding actually exists. And I hope now that's done. Now, so we can move on to the next embedding type. Okay, so now we come on to the QAOA embedding, which is the embedding based on a very popular algorithm, which is quantum approximate optimization algorithm. Again, if you see, you can have your data type as integer, float, or complex. And the highlight of this particular embedding is that this embedding is trainable. That's the most important thing. That's the takeaway from it. Now I'll just try to help you to refresh the QAOA. So we can just these are the terms. Just pause the video, just look at it, and here, here this is the basic algorithm. It will help you to refresh. If you actually want a great explanation, I would suggest you to go to the Qiskit textbook, Qiskit explanation for the QAOA algorithm. They explain it very well. It's a direct to the point explanation and really easy to understand. Okay, so with that said, let's try to break down of this particular coding. So what is this encoding anyway? So there are like two parts in the encoding. The first is the feature encoding, and then the second is NSAR. Okay. So the first, whatever feature vector you give, so it will just use those values as input to the rotation Rx rotation gains. Now this is very similar to the angle embedding that we have already seen. All right. But the next part that comes here is this particular ZZ gate, which is trainable, which is actually represent like this, but the important part is that it's trainable. Okay, then the next is you have a local field which is again trainable. Then here you have a choice on what type of local field you want to give. So you can have X, Y, or Z, which basically represents RX gate, RY gate, or RZ. Now I have a little picture over here that could probably help you to understand it better. So you can see, like, first we have this RX gate here, that takes these values x1, x2, and x3. Then you have this theta values for z. It's just here, denote z gate. All right. So since this embedding is trainable, it's very obvious that it will be having weights. Then again you have this ry gate, which represents the local field, and again this is also trainable, and that's why if you see, it also has these values theta 5, theta 6, theta 7. And then at the end you apply this rx gate again, rx, all these rotation gates again, and then you continue the layer. So if you see, we actually have two layers here for this particular picture that you are seeing. And talking about this header mode and RY gates in the below, so don't worry about it. It's just because the number of features is less than the number of wires, so it's just for that. So nothing to worry about. Okay. So with that said, let's move on to the coding part. So first thing, as usual, if you see here, we will define the default.qubit device. Nothing so special. And then coding part is simple. You just do QML.QAOA embedding. You provide your features and weights. Remember, this is a trainable embedding. Then you give your wires, and this is your local field. So what type of local field do you want? Do you want it Rx, Ry, or Rz gate? You give that to this particular string value, and yeah, so that's it. Super simple. So once that's done, what you can do is just create a feature vector. What I've done here, just to show you, I just took one complex value and one integer value, and now since you need to provide weights as well, so what you do here is that you do qml.qaoembedding.shape, and you provide how many layers you are planning to give, okay, and then how many wires you have. So just give that, you will get the corresponding shape of the weights that you need to have. Then you can just randomly initialize your weights, all right, and then you have your weights. So let's make this work. That's done. Now what remains is just execute this. You see I've got one nice a good tensor here as the output, and if you just want to visualize the circuit, this is what the actual circuit looks like. Let me just close this. So nah, it won't work, does it? So yeah, so this is the embedding. Now comes the important part of training the embedding. Okay, again that's super simple. Again, I just try to write just code for it, and whatever you are doing is nothing uh, different here. Just again define a function. I'm again using QAOA embedding and the expectation value, poly observable, uh, everything simple. And now comes the training part. So what I'm doing here is something very simple. If we are, from some we have done machine learning or deep learning, then it would be super simple to understand. So I'm defining a optimizer here. I'm defining the number of steps for which I want to optimize, and then I'm just doing optimizer dot step. So I'm passing this function for the trainable QAOA, and I'm passing the weights. So the weights will be optimized based on the values, and if I just run this, and you can see for the number of steps that I have defined, it has tried to work on the optimization, try to change the values. Not much of difference I see. Yeah, it's tried to optimize. Again, because this is no particular, data or weights, I just randomly just try to show you how it would work. And yeah, that's it for the QAOA embedding. Now let's move on to the next one. So now let's talk about the IQP embedding. Again, you can have your data type as integer, float, or complex values. Doesn't make a difference. And here again, it's like the same thing that we have been doing so far. We define the device. Now, then we define the function. Where we define the embedding. The coding part is simple. It's this QML.IQP embedding. The only slight change here is the end repeats here. Okay, so what's the end repeats anyway? Uh, if you see the picture here below, what I've just printed out, you see like it's based on the IQP circuit. Okay, so that's where the name comes from. So what is this IQP circuit anyway? So in simple terms, you first have these bunch of all these header miles applied. Then you apply diagonal gates, which in this case is just simple RZ gates. So you take your features and you apply it. So you can see like I am providing 7, 8, 9 here. So you can see like it has been the value that's given to it. And then you apply the ZZ gates. Okay. And that's the highlight of this thing, that what you are encoding here in the ZZ gates is actually the product of the features. So if you see here for the 0th wire and the first wire, this is 56, which is nothing but 7 into 8. All right. So when you are then trying to link wire number 0 and wire number 2, then you have the value 63, which is nothing but 7 into 9. And then when you have this y number 1 and y number 2, you have 72, which is nothing but 8 into 9. So it's also encoding the product of your features. All right. So that's the highlight of it. Okay. So let's just run this and see how it works out. Okay, it works out well. And if you see, yeah, that's it. Uh, okay. So now one more thing that you can do here with this particular embedding is change the pattern. So if you see the first 0 and the first wires are applied for the ZZ gate, then you have 0th wire and the second wire and so on. So if you want a custom pattern, then that's also what you can do. Okay, so you can just define a simple custom pattern here. I just tried it, and like yeah, so you try that and you provide that custom pattern in this particular argument here, pattern equal to custom pattern. And again, the number of repeats just kept one. You can repeat it for more number of times. So let's try that. Let's keep it to 2. And yeah, now I think we are ready to go. And one thing here is just expectation value for the poly z observable. So again, like this is nothing but this is the same thing of what we were doing for only one wire, one qubit. But here what we are doing is like for all of them. So that's why this list comprehension comes into the picture. That's the only difference. Okay. So with that said, let's just execute this thing. Okay, and if I just want to show you how it actually looks like, and you can see like it's repeated for twice, like for 2 times. Okay, and you can see the pattern is like now what I've defined. So for 0th one, then 0 and 2, and the first and the second. All right. I hope that's kind of like super simple to understand. Yeah, and this is it for this IQP embedding, and I hope like you are aware of this thing now. And actually, it comes from a research paper. And so I will also link that paper in the description. So if you want a more detailed, understanding of this particular embedding, you can go through the paper. But the motive was to let you know that this thing exists. That was the only motive. So with that said, let's move on to the last embedding type, which is the squeezing embedding type. So let's move on to the last embedding technique, which is the squeezing embedding. And the name comes from the squeezing gate that we are using here. So now if you remember, this is very, very similar to the displacement embedding that we have seen previously. The only difference is here if you see the 1 by 2 term, all right, and the squared operators. That's a very big difference if you see mathematically. And in the official documentation, they are showing this particular uh, equation. So I'm showing you that it's just substituting z equal to r into e to the power alpha. Again, you have this default.Gaussian as your device and not the default.Qubit that we use for the other techniques. So now let's try to make it work. Again, it's super simple. Define the device default.Gaussian, and then you directly use QML or squeezing embedding. Now you define your data, you define your number of wires. Again, now this thing goes the same as it was for the displacement embedding one, right? If you define amplitude here, the method is amplitude, then your features will be, used as for the value for R. Otherwise, if you are, specifying this method as phase, your feature values will be, considered as the values for phi, and the opposite thing will be the c value for c that you provide, it will be considered for the opposite term. All right, again the expectation value for the number operator, which is the photon number. Yeah, so that's it. If I just run this and if I make this draw to go, yeah, so yeah, that's it. Now I really hope that this video was useful to you, and you at least now know a few techniques that you did not know previously, maybe. And the links will be in the description there if you want, the better understanding of the few of the embedding techniques that I've described. And yeah, like that's it from this video. And we will be back with more videos on quantum machine learning. And until then, just try and work on quantum machine learning and follow the channel if you like this type of content.